And our presenter is Jens Klump.
And of course, I want to acknowledge my co-authors on this work, who have contributed to this, and the institutions NCI, the National Computing Infrastructure, Curtin University, and the IGSN. So why do we do this? Samples are quite important in the natural sciences, as they are the ground truth for many of our investigations. And when you ask people what is a sample or specimen or whatever they want to call it, you immediately get into long discussions. And we recently had those in Canberra in an international symposium. And one of the ways of describing it we came up with was a sample is a thing or subset, which can be real or virtual, which is intended to be representative of a larger thing or set. And it is created or selected for the purpose of making observations or measurements to determine the properties, traits, or qualities of the larger thing. And in the geosciences, samples are very important because that's what we often work with. But they can also be very difficult and expensive to obtain. So you have to go to exotic, faraway locations, or it's down a mine, or some other reason why it is difficult to get there. And then with advances in analytical technologies, we may want to reanalyze a sample. And because we work with them all the time and derive data from them and interpret them in the literature, they become important reference points for the data that are derived from them and the interpretations then of these data. And because of this important role and the need to sometimes go back to them, it is important to potentially have access to samples. Because we might need to verify observations or concepts. So you might have to go back and take one of the samples from one of those repositories, look at them again, or reanalyze them. In the case of biodiversity, often it's the case that you have something that you collected in the field and you want to compare your concept of a species with the holotype specimen kept in the collection. And so it is necessary to go back and have a look. And sometimes you can take these samples to obtain new data on the same sample because we have new analysis techniques or new questions. And the sample location may no longer exist. Especially in mining, this is the case. So an ore body was discovered, described, then mined. And when you want to go back to it, there's just a hole in the ground. There's no way to go back. But there can also be good reasons not to disclose this information because it's an endangered species, it's a culturally sensitive site, or for many other reasons. But the standard is open, but there might be good reasons to be careful not about what you want to disclose. To have this not just hypothetical, I took one example that I experienced myself. Here, having some identifier would have really helped me. What I was doing here was running numerical models of seafloor and extracting natural gas from the seafloor. And I was taking physical properties from the literature. And when I presented this work to my colleagues, they said, your values are not plausible. Where did you get them from? I said, yeah, from this paper. And they said, no, we don't believe this. So I meditated over this map to try and understand those cryptic numbers in the inset, to find out how could I find the ground truth to what the authors of this paper had reported. And then I realized that these were boreholes from international drilling programs. And because I knew something about drilling programs, how they're organized, how they're run, how they store their data, I could trace that path back and actually find the original data as they were measured on that drill ship and verify my claim. So that worked. But often enough it doesn't. And this is a map on the left of samples from the EarthCam database labeled M1. M1 can be anywhere in the world and can be anything, as you see on the right-hand side with the screenshot of the list of what it could be. Apparently, researchers working in Japan have a particular liking for M1, but it shows you that often, because outside of the drilling programs, the naming is not standardized, M1 seems to be a popular choice. It can also be the other way around. This is an example of a piece of ocean floor basalt dredged from the East Pacific Rise that has been reanalyzed many times and has received a number of names, all listed on the right-hand side of the slide. So again, this makes it difficult to identify what you're actually dealing with. So if you want to compile global data sets of something related to samples, this approach doesn't work. One of the questions that I get asked quite often in this context is, why didn't you use DOI? Because they are around, it's an established system. Yeah, it is an established system now. When we started with IGSN, it wasn't so established. DataCite had not yet been founded. So when I approached the TRB Hannover, who were running the precursors of DataCite at the time, they said, very nice idea, we like it, but it's out of scope of our service. Since then, we've had numerous conversations. At the moment, we still keep things separate, and one of the reasons is that our metadata requirements for samples are quite different to the more bibliographic metadata required by DataCite, although there are overlaps. More importantly, the syntax and governance model that we use to run IGSN is more suitable for humans writing identifiers onto labels rather than machines dealing with this exclusively. But technically, IGSN is based on the handle system, as DOIs are, and that makes the two systems compatible. And the technical development is very closely aligned with DataCite. It's actually a clone of DataCite, and also the organizational model is a clone of DataCite. So in an overview, what does IGSN do? It provides identifiers that are guaranteed to be unique, because we use a hierarchical governance model, like assigning IP addresses, that you have only a certain part of the thing that you're allowed to change. It facilitates internet-based discovery and access to physical samples, and that's web application and programmatic access to sample metadata catalogs, and then networks with sample repositories and data centers. IGSN then also ensures the preservation of sample data and access to it, because we have certain rules. If you want to play along, then you have to play along those rules. And having IGSN aids the identification of samples in the literature and also of the data derived from these samples. If you want to try it out, these two examples that resolve, one is from an international drilling campaign, which was run in Scandinavia, and the data are hosted at GFZ Potsdam. And the other one is a sample from the Geoscience Australia collection. So in practice, you have these different ways of dealing with it. You can type it into a browser, or you can scan the QR code, which basically gives you handle URI, which then resolves to a landing page describing the sample. So pretty standard approach. What can it be used for? So we use it for geological and other materials, starting with rocks, but since it has expanded into water, biological materials, also what we call collections, which are groupings of samples, which can be just a box, or it could be things along a borehole or something, but things that belong together. It can also be sampling features, that can be boreholes, outcrops, or something, which is not an object, but the feature that the sample was taken from. Because they're very intimately related, we didn't want to wait for somebody to set up an authority to name features in the landscape, but rather identify them ourselves. And what is quite important is that in the metadata that we collect with those samples, there's an element called related identifier, similar to what DataCite has, where you can relate one object to another and describe that relationship. So this is how we aggregate collections and how we identify subsamples taken from parent sample, etc. In CSIRO, we use IGSN to track samples through their life cycle. This starts in the field, and where we have an Android-based app that we use to collect the metadata as we collect the sample and identify the sample at that point. When the sample moves to the lab, the IGSN helps to identify the sample and tie the data that were derived from the sample to this object. And then once it's gone through the lab and is stored in the repository, we use it to identify the object itself, the collection it belongs to, help with the whole storage logistics and manage the samples and track them. So as a little aside, this mobile app turned out to be really useful. It was something that was developed for archaeology to help them in their field campaigns in the context of the FAMES project run by, coordinated by Macquarie University in Sydney. We adopted that app quite successfully, and it now replaces paper notebooks for certain types of investigations. What our researchers like very much is that we have equipped them with a portable server that they can put on the truck, take it out into the outback where there's no internet connection, and then synchronize the data from their apps to that server. And once they're back at the field station, they can download it, analyze it, QC, whatever. And when they come back to civilization and have internet, they can upload it to our servers at home. So this app is now being used for water sampling, vegetation sampling, and also for rock sampling. IGSN start to appear in the literature, and to make this transition easier, we have had quite a number of conversations with publishers. Elsevier and Copernicus are already using IGSN. They have implemented it. And then there's the Coalition for Publishing Data in the Earth and Space Sciences, COPDES, who've issued a statement about how to identify samples in the literature, in the geological literature. There's an example further down the page from Geochemica at Cosmochemica Acta, for instance, about shales somewhere in the Appalachians, and all the materials in this study have been identified by IGSNs. So just to show you it works, it's there, it's not hypothesis, but this gives you an overview of the power of linking all of this together. So there's this specimen identified by an IGSN here, a piece of kaolinite, and you can find it in our catalog for mineral reference spectra. There's a spectrum derived from it, an optical spectrum. The data are stored in the CSIRO data access portal identified by a DOI. You can download those. Both are linked through the related identifier element. And then the spectrum is part of a publication which interprets a number of optical spectra from minerals. And this publication is identified with the DOI, refers to the data set, and more data sets. So it's not only the identifier for the object, it's also the linking between those objects that's important. This is a cartoon overview of how the system itself works. There's some client application. We have a handful within CSIRO that speak to what we call an allocation agent. So CSIRO is its own allocation agent, and the allocation agent then registers the IGSN with the IGSN central. And registering is here an important keyword because it's not a request. You don't request an IGSN, you register it. So the reason why we do this is so you can use it offline, you can identify things out in the field without internet access, and once you come back to internet, you can register it. You don't have to wait for a response to your request. And different to the DOI DataCite system. We don't deliver all the metadata in one go, but the allocating agent offers rich metadata through an OAI PMH interface. And the reason for that is that samples are all quite diverse, so there's no one size fits all, and OAI PMH allows us to serve several metadata schemas alongside each other instead of having to compromise on one. The technical base you can find on GitHub. It's basically a fork of DataCite. So it's built upon an existing technical base and community, and incorporating the handle system, and developed in close alignment with DataCite. What is different to DataCite is the governance model that I already mentioned. We use a hierarchical delegation pattern. DataCite has that, but doesn't use it to the same extent. What we do in this pattern is that each IGSN agent is given a namespace and then can delegate sub-namespaces for registration of IGSNs to its clients and subsystems. So as an example, any IGSN starting with AU is governed by Geoscience Australia. Any IGSN starting with CS is governed by CSRO, and we have delegated the namespace CSCAP to the Capricorn Digital Footprints project, which is a fairly large collaborative project. And we have delegated the namespace CSRWA to our rock collection, and so on. And then our clients, Capricorn Digital Footprint or the rock store, only have rights to mint and define IGSNs in their particular namespaces. What they then do is their responsibility, but they will not interfere with the others. It becomes challenging when things start moving between organizations, and one of the cases is when you involve a lab. In our case in Perth, that is the John DeLater Center for Geochemistry, or our service provider Lab West. And if there's an IGSN available, it's easy, they just continue using that. If it's not available, John DeLater Center assigns an IGSN. The second interesting case is when you do subsampling in the lab, and this is when things become a bit more tricky because there's a bit of a branding issue involved, and sometimes you want to keep that identity, sometimes other people don't care so much. But the main thing is that for the subsample, you should register new IGSN to be able to identify the subsamples. IGSN is a global organization. It's the IGSN Implementation Organization is a charitable organization incorporated under German law in Potsdam, Germany. And at the moment, IGSN EV has 19 members on 5 continents. But I'll come back now to the Australian implementation of that. The first implementation was at CSRO. CSRO became a member in 2013, and at the moment we're using IGSNs in the rock repository of the Australian Resources Research Centre for rocks, minerals, soils, for our national collection of mineral reflectance spectra, which then identifies minerals, rocks, synthetic materials as well, and in the Capricorn Digital Footprints project, where it identifies water, vegetation, soil, rock, and regolith. And we're looking at expanding this to future use cases in our soils collection and in the national insects collection. The second implementation in Australia was Geoscience Australia. Geoscience Australia is the federal geological survey for Australia. It became a member in 2014, and all the samples in the GA collection are now identified with IGSNs by just appending their identifiers to their GA names, to their AU namespace. And GA have registered 1.6 million samples out of 6 million total. So when we look at the global implementation, there's 6 million IGSN registered, 1.6 million by GA. identifying rocks, mineral separates, thin sections, fossils, also some crude oil I've discovered, and other interesting materials. GA is also the registration agent for the geologic surveys of the Australian states and territories. Our third member in Australia is Curtin University, who became a member in 2015. They currently use this for the John D. Later Centre for Geochemistry. They're being supported by the library in their implementation, which I think is an interesting model. The lab is interesting because it's an intersection of different users of the John D. Later Centre itself, CSIRO, the University of Western Australia, and the Geological Survey of Western Australia, who work together in the Natural Resources Research Precinct. To set up this implementation was supported by the ANZ Major Open Data Collections project. And with another grant from the Research Data Services in NCRIS, we were able to set up the Australian IGSN portal, which uses the OER PMH harvesting service to harvest from the Australian allocation agent and then aggregate all their catalogs into one common portal. So the status of implementing IGSN, it's work in progress. Active registration agents worldwide are CSIRO, Curtin University, Geoscience Australia, GFZ Potsdam, Columbia University, the University of Bremen, the German Federal Geological Survey by proxy, and the US Geological Survey by proxy. There's a bit of a problem of getting government institutions to join a foreign charitable organization, so they sometimes have to go through a proxy. And our future outlook is to build a developer community around IGSN, to document best practices and build reference implementations of services to help new allocating agents to come on board. Expand identifying and linking to objects in other domains, and to then eventually see other domains start reusing IGSN technology. So in summary, samples are ground truth. I hope I could convince you of that in the natural sciences, and they need to be identifiable and accessible. IGSN provides a global, unique and resolvable persistent identifier for those samples. In Australia, we introduced it through a collaboration of national labs, government agencies and academia, and we now see that IGSN is spreading to novel use cases. And if you want to find out more, here are URLs to follow. And thank you very much for your attention.
Time for questions. Once again, please wait for the microphone.
Hi, my name's Susan Lafferty. I'm interested, in the public portal, anybody can go and see pictures of samples and read the data about them. Is that right?
The public portal is an aggregation of the catalogs served, so there are no pictures in that portal, but from there you can go to the landing pages at the respective agents, and then they show whatever they decide to show.
I had a question. This obviously seems like a sensible and straightforward approach. Are there other competing ideas or approaches in the same space?
There was a fairly big effort in the life sciences, especially biodiversity, trying to introduce the life science identifier, LSID. It's difficult to find out what the fate of LSID will be, but it seems to me that this approach has been dropped and they have now switched to cool URIs, HTTP URIs as identifiers. Then all other approaches that I've seen relating to physical objects if they're not monolithic, use HTTP URIs, but nothing like this.
Other questions? Oh, maybe. Oh.
Hello. I had a question about the namespaces. To me, some of the examples you showed, I didn't notice any sort of delimiter in the namespace to the sample. Would that be potentially a problem if you have many organisations joining up?
Sorry.
I might get you about this one afterwards. Actually.
But
so, like, say another organisation wants to use AU or a namespace that starts with AU. That I just noticed those two-letter namespaces seemed like limiting the potential number.
Well, yes, that's very limiting. But we also thought that we wouldn't have that many allocating agents. If you in the first iteration of this whole system, there was this idea of giving namespaces to a much larger number. In the very first idea, there was the idea to give namespaces to every investigator, but then we found out that in that system, the namespace wouldn't be available to even identify all geoscientists known to the National Science Foundation. So namespace exhaustion is a real concern, and so we have these checks and balances on how we allocate those super namespaces and the sub namespaces.
Any other questions? Well, perhaps we are ready for lunch. Thank you very much.
Thank you.